I think we have got a healthy dose of Spark UI over the duration of this particular course. We have seen all the different tabs like the jobs tab, the stages tab, the executor tab, environment, the storage, and the SQL and data frame. Now, as we are approaching towards performance tuning and we have finished almost all the transformations and actions that I was supposed to tell you, it is a good time to talk about the physical plan operators that you can see in the DAG visualization. And the physical plan operators would be typically seen in the SQL and data frame tab, wherein you see the entire DAG of the Spark application. I'm not talking about the stages tab. There the name might be a little different, but you can correlate the DAG visualization in SQL and data frame tab with that of the DAG visualization that is available in the stages tab. And we have seen a lot of operators in the DAG visualization. Let's look at those operators. What are the physical plan operators? In this particular topic, I'll be explaining these physical plan operators that we see in the DAG visualization. And after this, you will be equipped enough to look at the Spark DAG in a different way. You can understand exactly what is happening in the entire application, and it'll be helpful when you go to the explain topic and later on when you discuss performance tuning. So let's look at the physical plan operators. And before that, I want to do a recap of hash table because the hash table concept would be used here as well in the operators. As you already know what a hash table is, that it is an in-memory data structure and it stores and retrieves data in key value pairs in a very efficient way because everything is happening in memory. What the algorithm does is that it creates multiple buckets, and depending on the values of the keys, the rows would be associated with exactly one bucket. Now after that, when let's say you are doing a lookup or aggregation or anything of that sort, you just provide the key and you know which bucket that key is present in. And this is the fundamental concept of lot of operators or lot of operations rather that happen in Spark. First is the hash aggregate. So as you can see, we have the term hash here, which means that the hash table or the hash bucket would be used in this operation. It is used to perform aggregations using in-memory hash tables. When I say aggregations, there are multiple aggregations that are available. We have aggregate functions like sum, average, minimum, maximum, sorting, partition by, etc. And all these operations use in-memory hash table. And hash aggregate operator is used before and after shuffle. So if you are using group by, then there would be a hash aggregate. If you are using sum or average, minimum, maximum, count, window functions, etc., hash aggregate can be used. Let's look at how a hash aggregate plays out. So let's say this is the data frame that we have, and we have this country column and count, which is the number of flights. These two are two columns. Of course, I'm not showing all the columns, I'm just showing you two columns. There are multiple countries here, India, USA, and Spain, and the value is different. Now, let's say you want to do a group by based on country, and then you want to do a sum of flights, which is actually the number of flights. Now, what would happen, how this operation would be performed internally in Spark? Because you have group by and sum both, Spark would create a hash table, and the hash table would contain the key or the distinct values of the key and individual hash bucket. Let's say we have only three buckets because we have three countries. Let's say Spark creates three buckets. One bucket is for India, and another bucket is for USA, and the third bucket is for Spain. So this is the three different bucket which has been created in the hash table based on the countries that we have. Obviously, the number of countries would be much higher and the number of buckets would be lesser than the number of countries. But it does not matter because the moment you provide the value of a key, Spark can find out, or the hash table algorithm can find out which bucket that particular value is being stored at. But here what we are doing an aggregate function like sum. This hashing algorithm or hash bucket algorithm or hash aggregate algorithm, whatever you might want to call it, will go to the first row whose key value is India, and the summation that you want to do or the addition that you want to do is the number of flights. So because it is India, it will go to the first bucket and store the value 10. That is the first operation. Then it will go to the next row. It will see, okay, the country is USA, It'll go through a hash function and the value is 20. So the value 20 would be stored in the second bucket for country USA. Why second bucket? Because if you hash the value USA, the hashing algorithm will find out that it belongs to bucket number 2. Then for the third row, it is again India and the value is 50 this time. And we are doing a sum. So what would happen? It will go to the first bucket because the country is India. And instead of 10, it will be 60, which is summation of 10 plus 50. So it will store the cumulative value of the function that we are using. In this case, it is sum. If you use average, of course, it will be 10 plus 50 divided by 2, which is 30. If the function is maximum, then the value would be 50. If the function is minimum, then the value would be 10. If you are using count function, then the value here would be 2. All right. After this, it will go to Spain, and it is a completely new key value, which is Spain. So this row would be stored in the third bucket with the value 30. Then the next column is also Spain, but the value is 30. So it will go to the hash bucket and it will get inside of this particular Spain bucket, which has a key of Spain, and the value would be increased to 60 because 30 plus 30 is 60. Finally, it will go to the last row, which is having a value of India in the country column, and the summation column has 20. So it will go to the first bucket and then it will increase the value to 80. So this is what hash aggregate is. It uses a hash table to do the aggregation. And as you can imagine, the hash table will have buckets, and for each key, it will have certain buffer also in memory. Of course, the buffer value would not be that high. It does not need too high value of buffer, but for each key, it will go to the bucket and fetch the current value and perform the aggregate function, whichever is given. So if it is sum, it will add. If it is average, it will find the average between the two. If it is maximum, it will find the maximum value between all the rows that have gone. So that's what hash aggregate is, and you'll see this operator a lot of times in your Spark UI. We'll try to execute a complex SQL statement and then we'll go to the DAG in the SQL and data frame tab to see what operators we find. Now, so far so good because we have this hash table which is in memory and everything is happening really fast. The performance is good, but of course there are certain limitations. We do not have unlimited amount of memory. There is only certain amount of memory which is available to a particular application, and that memory would be taken from executor, by the way, because these will happen on all the partitions that are available in all the executors. Now the question is, what if the memory is not available anymore? What would happen? So in that case, the data would be spilled to disk. So the remaining hash table would be written to disk. The existing hash table which is there in memory will be there, but the additional values would be written to disk. That is called spilling of records or spilling of memory. So because of memory limitations, this might happen. Then you have another operation which is called sort aggregate, and it is also used to perform aggregations using in-memory hash tables. It is also used for aggregate functions before and after shuffle, like distinct, order by, etc. But there's an additional phase which is a sort phase. Of course, there's an additional cost because of this additional phase. Now the sorting happens in memory itself. It does not go to disk unless there's not more memory available. And optimizer might not choose it if it sees that hash aggregate is better. So what would happen in this case? Again, I'm taking the same example. We have countries and number of flights. So before creating the hash table, it would undergo this sort phase. And here the records would be sorted. So as you can see, the records are sorted based on the value of the country. So if first India, then Spain, then USA, obviously depending on characters. Alphabet I comes before S and alphabet S comes before U. That's how the sorting is. And accordingly, the values of those corresponding columns will also be sorted. The sorting would also happen in memory unless there is not enough memory available. In that case, the sort phase can also spill to disk. Anyway, after the sort is done, then the hash table would be created and the output would be similar. So maybe there are 3 buckets for 3 different countries. First India, next one is also India, third one is also India, so it will keep on adding. Now the moment it finds Spain, we know that we do not have to go to the bucket for India anymore, because as it is sorted, we'll not have the country India coming anymore in the result set. Same is the case with Spain. Once Spain is over, the value of Spain will not come anymore once we get to USA, because it is sorted. So this is what sort aggregate is, and in most of the cases it might happen that Spark is choosing hash aggregate rather than sort aggregate. And just like hash aggregate, sort aggregate can also spill to disk if there is not enough memory available. Then you have sort merge join. We have already seen sort merge join. This is the default join strategy, and it can be changed using Spark SQL join prefer sort merge join configuration parameter. And it is a Spark internal join that you have already seen. Then you have broadcast exchange. It is a little different. First of all, broadcast exchange is used in broadcast hash join and broadcast nested loop join. So this operator happens before both broadcast hash join and broadcast nested loop join. The reason is because we have broadcast in both the cases. So that's why I have this broadcast exchange. And it can be configured using the Spark SQL auto broadcast join threshold, which we have already seen. Now, how the process is. So let's say I have this driver and 3 executors. So this is the large data frame, and executor has partition number 1 of the large data frame, executor 2 has partition number 2, and executor 3 has partition number 3. Of course, I'm keeping it simple. I'm not showing all the partitions. Let's say each executor has only one partition. Similar would be the case with the small data frame also. So executor 1 would have partition number 1, executor 2 will have partition number 2 of small data frame. Same would be the case with executor number 3. Now what would happen? All the partitions of the small data frame would be sent to driver and it will be consolidated there. So now the driver would have the small data frame with all the partitions. So essentially, driver will have the entire small data frame. And after driver gets this small data frame and it consolidates all of them, it will serialize the data frame and send it to the executors. Now, all the executors will have the small data frame in its entirety, not only individual partitions, but the entire small data frame, because it has been broadcasted by the driver node to all the executors. So this is what broadcast exchange is.